Hey, we've got Ben Seaman with us. I wonder who else we've got here. Mohammed's here. It's Ben and Mohammed right now. Nicholas is here. And Ashley's here. Okay, I guess we're almost ready. Let's see. I need to adjust this a little bit. There, that's better. Thursday, October 29th. Got some glare going on there, but I don't guess it's the end of the world. Maybe if I change this, that might be too dark. Maybe that's a little better. That's okay, I guess.
And
Yeah, good morning.
how are
Uh,
you?
I'm doing okay. It's raining here. What about where you are?
Same, raining here.
Yeah, raining.
So, I have a question for you.
Sure.
So, are you gonna teach dynamics next semester in the spring?
I've got some very sad news for you. I'm retiring.
Okay, so you're not gonna teach any class next semester?
You know,
Or is there any?
I really haven't decided yet, but
I wish you if you can stay one more semester and teach me the dynamics class. That's the only class I'm left with.
I would love to, but I can't promise you anything. I don't really know what I'm going to do, but I've been teaching 50
I
years.
know.
It's probably time for me to quit. I've enjoyed it though. I kind of hate. I tell you what, Mohammed, if it weren't for this COVID, whatever it is, I didn't want to retire yet. And I would love to teach you dynamics next semester, but I'm kind of fed up with this. Uh, what do they call it? Stay at home quarantine, wearing masks and all that jazz. I don't like it. How about you? Do you like it?
Well, me too, no.
I think I lost Mohammed.
No, I said no, I also don't like it.
Yeah, I don't like it. No, I'd much rather see you guys in person. But
Well, I will request you if you can teach dynamics next semester and then you can maybe take days off.
I wish
Just
I
one more
could.
class.
Yeah, I love that. Hey, I'll give you some warning. Whoever teaches that dynamics, that is the hardest class that we have. Dynamics is harder than thermo, I think. Have you had thermo yet?
Yes, I'm in your thermal class as
Yeah.
well.
Well, it's pretty hard, but I think dynamics is the hardest, but maybe not. People are different. Some people might argue with me and think thermo is harder. That's just my opinion. Well, we need to get started, guys. It's 9:30. We're going to get started now. Here's your last chance to ask me anything. Otherwise, I'm just going to have fun and tell you what The topic, we're going to study plastic behavior now.
Can you go over the problem F6-11?
You want to look at that? We can
Yeah.
look, yeah, we can look at that. This is, Mohammed wants me to look at problem F6-11. Let me find it, hang on. You don't know what page it's on. Never mind, I found it. I found it, it's page 302. First thing we have to do is get the moment of inertia. See, we're going to use this equation here. But we need this I thing here. They call that the area moment of inertia. We need that. Now, let's see if we can get that. Let me draw this. It's 200 by 20. Okay, here we go. 200 by 20. Everything's 20. But now, wait a minute, that's longer. That's 300. That goes down to here. Yeah, that's 300. This is 200. And then this one is the 200 again. Okay. Now that's 200. And these little pieces here are 20. These are 20. And this here is 20. And now be careful now, though. This 300 goes all the way to the very bottom and all the way to the very top. You know that? According to the picture there. Okay, now there's a hard way and an easy way to do this. Let's do it both ways. Now the easy way is you take this whole thing here. Yeah, there we go. See that whole thing? The moment of inertia, that whole thing is 1/12 times 0.2 times, in this case, it would be 0.34 cubed, isn't it? Look at the flap of your book. Doesn't it say 1/3 or 1/12 BH cubed? 1/12 base. Well, that would be the base. And see the height, it would be 0.34. Because it's, no, I got that wrong. It's just 0.3. Just about goofed up there. You see this whole height is 0.3. Okay, and then what you do is you subtract these parts that aren't there. You see this? You see this rectangle here? We're going to subtract that. And then we'll subtract this one that's not there. Okay, let's do that. Minus 1/12. Well, there's really two of them, but the total length on them is 180. And the height of those, now watch it, that's going to be 0.26, isn't it? See, if you take 300 and you subtract the 20 and the other 20, that makes 40. 40 from 300 is 260, isn't it? Yeah. If you subtract 40, no, I'll get this right. If you take 300 and you subtract 40, see there's 20 and 20, you get 260. Yeah, that's right. Okay, guys, this is going to be it. Now that's the easy way. Here, let me do that and get my answer just a minute. Well, I got an answer. I got 1.8636 times 10 to the minus fourth meters to the fourth. Now let's do it the hard way. Now to do it the hard way, we're going to use the parallel axis theorem. And we're going to break this into three pieces. We have a horizontal, they call it a flange. And we have another horizontal flange. And then we have the web. So we'll just add the three up. Now for this horizontal flange, they spell that F-L-A-N-G-E. What you got is 1/12 the base, which is 0.2, times the height, which is 0.02 cubed. But see, that would be the moment of inertia about the center of that flange. And to use the parallel axis theorem, we need this distance here. And so what you do is you take the area of the flange, which is 0.2 times 0.02 times that distance. Now let me think. That distance will be, well, it's 300 there, and it'd be 150. Then you need to subtract 10 from it. What's 150 minus? It's 140, isn't it? And that's squared. Remember the parallel axis theorem goes like this. They call that the parallel axis theorem. And see, we got this here. This is right here. That's the moment of inertia about the center of that flange. And then you take the area of the flange, which is 0.2 times 0.02, right? Times the distance between this G here. We call this G. You can call that point A if you wanted to. That distance, I think, is 0.14 meters, isn't it? Did I do that right? Yeah, I think so. But the thing is, there's two flanges. So what you need to do is you need to multiply that by 2, because there's 2 of them. There's one up here and there's a bottom flange. But you're not done yet. You have to add the web. Now they call that the web. And the web is going to be 1/12, 0.02. Now watch it now. It's going to be, that's the 0.26 meters cubed, isn't it? Let me think now. 1/12 the base. The base of the web is 0.02. And the height of the web is, that's supposed to say 0.26. It's 0.26 from here to here. Yeah. Okay. Okay, now here we go, guys. We're going to take this here and we're going to add all that up. Then we're going to multiply it by 2. And then we're going to add this web to it. And let's see what we get. Here we go. Well, I got an answer, and here's what my calculator says. Well, how about that? I got the same answer I did the easy way. This is the hard way. This is the easy way. But I'm going to wait till I hear a couple of uh-huhs. I want you to add this up, multiply it by 2, and then add to that. And if you get this, I want to hear an uh-huh.
Yes, I got the same.
Yeah. Now, let's talk to Mohammed here. He's the one that asked about this. Mohammed wanted me to do F611. It's on page 302. Mohammed, which do you like better, the easy way or the hard way? Which do you like better?
The easy way, I like it.
Me too. I like it better. It's kind of nice. But you need to know, now here's the thing. This hard way always works. The easy way, you got to be careful with it. It only works if you have a symmetrical thing like we got there. That's it's kind of got symmetry, doesn't it? It's got symmetry about the x-axis and about the y-axis. It's got symmetry. Be careful about doing it the easy way if you got an oddball looking thing. But it sure works nice if it's symmetrical. Okay, Mohammed, are you happy with that?
Yes, sir. Thank you.
Yeah, oh, wait a minute. We're not done yet. They wanted us to do something else, didn't they? Let me see here, just a minute. Oh, they wanted the maximum bending stress. So let's finish the problem for them. All we've done so far is we've gotten this right here. They want this here. They want the maximum bending stress. Well, see, that's going to occur where this y is maximum. Remember what y is? It's the distance from the centroid. That's your y right there. And the maximum y is going to be either at the top or at the bottom. Now, if you're at the top, you get compression, and at the bottom, you get tension. So they come out equal in this case. And that's what they want. Well, let's do it. Here goes. Never mind the minus. The minus is just to help you decide. See, if the y is plus, That's plus, that's plus. That minus there makes it a negative. That means you got compression at the top. So at the very top, if you want the maximum bending stress, you put a little b there if that makes you happy. Maximum bending stress will be, never mind the minus, I'm just getting the amount. It's going to be, they gave you the M, now what they say, 50 kilonewton meters. Now the Y, they're going from the center of the whole thing, centroid of the whole thing to the very, very top is, well, it's 150. So it's 0.15. And we have the moment of inertia. We did it two different ways. We did it the easy way, and we did it the hard way. We got the same answer both times. So we know we're right. Okay, I'm going to shut up for 1 minute, and I want you to plug that in, and we're going to get the maximum bending stress. On your mark, get set, go. Well, I got an answer. Let me go to one of my excellent students here. Shane, unmute and say hello, please. Earth's calling Shane. Come in, Shane. Earth calling Shane. Come in, Shane. Uh-oh, coffee break. Samuel, unmute and say hello, please.
Good morning.
Hey, good morning. Samuel, have you plugged in these numbers and gotten this maximum bending stress yet?
Yeah, I got 40.2 megapascals.
You know what? I think you're right. Proud of you. Not much room there. Let's write it here. 40.24 megapascal. Good going, Shane. Now I want to hear an if anybody else got that. Anybody else get that?
Yes, sir.
Yay, good. Okay, well, let's look at the, thank you. Let's look at the answer book and see what they said. This was F611. I'm going to go back here and see if that's what they said. They said, .2 megapascal. The book says 40.2 megapascal. Yay, we did great. And we understand it. That's good. Well, let's talk about plastic behavior now. And let's pick a little simpler cross section to work with. This is all in your book. Let me show you where it is here. This is on page 344. I'm going to erase all this if it's okay. Unless you have another question or comment, I'm going to erase this. All right. Nobody said anything, so it's all going to go bye-bye. There you go. Okay. Now let's take a simpler cross section. Let's just take maybe we could take a 2x4. How would that be? Does that look about like a 2x4? I don't know. Yeah. There we go. Two by four. Now, if you put a bending moment on that, now the way the book draws these bending moments is they kind of go near like that. There's your bending moment. See, here's this 2x4. It might be easier for us to work in metric. Let's do that. Let's say this is 4 centimeters, and this is 2. Won't that be easier? And we won't have to fool with the English, which can be kind of confusing. Now, the way I write these bending moments is I draw them like this. I put a double arrowhead on them like that. But that means the same thing. It means the same thing. It's a bending moment. See, it's a twist this way. And a twist, if you twist something that way, it puts compression on the top and tension on the bottom. Here, I'll draw it for you. It puts a force. Well, it's a force. It's kind of a three-dimensional force on the top, but it puts a tension force on the bottom. I don't know if that makes a whole lot of sense. But see, it's maximum up here because, stress is equal to minus my over I. And the y is maximum up here at the top. Y is this variable going up this way. And so you get the maximum stress when you have the maximum y at the top. And there's a distribution going on if you have a moment like that. And the distribution kind of goes like this. See, there'll be a place down here where it's 0. It's kind of hard for me to draw this. It's really three-dimensional. But I'm trying. I'm trying to draw it. It's a three-dimensional thing. It's kind of messy looking, isn't it? But you have one down here also, but it's going this other way. It's going like this. I think I did that wrong. Yeah, I think it's like that. And see, it's a three-dimensional thing. Really hard for me to describe that. They have some nice pictures in your book of it. If you look on page, yeah, there's a really pretty picture of it on page 348. What this is this normal, it's a bending stress distribution, and they have a picture of it on page 348. You've got tension. Oh, now wait a minute. That one has tension on the top and compression on the bottom. I don't like that much because we're used to having compression on the top. Let's see if I can find another one that we like better. Wouldn't you know, they don't have compression on the top like they need to. Let me keep looking here just a minute. I'm not quite ready to give up on that. Why they would put tension on the top, I do not know. Sorry to waste your valuable time, but I wanted to show you this. We might have to live with my drawing, do the best we can with it. I think we're stuck with it. Now here's what's going to happen. If you make that bending moment bigger, remember we had a bending moment here. I like to draw them with the double arrows. If you make that bending moment bigger, you'll finally reach a place where you have the yield strength stress here at the very top, and you'll have the yield strength stress on the very bottom. And if you make the bending moment even bigger, by the way, they have a name for that. They call it the maximum bending moment. It's the maximum bending moment. We can figure what it is. Let me go ahead and figure it for you. If you wanted the maximum bending moment, and you need the amount, the minus, there'll be compression on the top and tension on the bottom. Don't get upset by that. And this is going to equal the maximum bending moment. Now that's the symbol for it. M with a little y there, a little capital Y. That's called the maximum bending moment. Now the y, in this case, if this thing has a base B and a height h, then that y for the maximum bending moment would be h over 2, wouldn't it? And the I would be 1/2 the base times the height cubed. If you had a rectangular, like a 2x4 like we have here. Okay, well then let's solve this. Here we go. We're going to solve this. We're going to do some algebra, and we're going to write the maximum possible bending moment. That's just before you start to go plastic. Do you understand? If you make that bending moment any bigger, it starts to go plastic up here at the top. But right now we're finding the maximum It's got another name. It's called the maximum elastic bending moment. It's still elastic everywhere. It hasn't gone plastic yet. And it's equal to, well, let's see, it would be 1/12 base height cubed. You'd have to divide by the h over 2, right? And then multiply by your yield strength, because that's what you'd have if you had a maximum elastic bending moment. Now let's do a little algebra and see what we get here. You would get 1/6 BH squared. I did a little algebra there. See, the 2 goes up in the numerator. 2/12 is a 6. You got a base. And one of these h's cancels out. And now, wait a minute now. What happened to my, there. There's your equation for the maximum elastic bending moment. Now, I want you to look in your book. They've got that equation in here someplace. Let's see if I can find it. I lost my page now. What page is that on? Can you find it for me? Okay, look on page 345. Do you see 1/6 BH squared sigma sub 1? Ta-da! We have just shown you how to get the maximum elastic bending moment. Now let's do it for a piece of steel. Suppose this is A36 steel. Go to the back and let's look up in the metric units the yield strength for A36 steel. Well, according to the back of the book, I'm looking in these tables back here. It says 200 gigapascal. Do I have time to write that someplace? Yeah, here we go. It says for A36 steel, 200 gigapascal. Okay. Now help me come down here. Do we have room? I think we have room. We have 1/6 the base. Now what we got there is 2 centimeters, so that's 0.02 meters. And the height is 4 meters, so that's 0.04 meters, which you have to square it times the 200 gigapascals. Okay, I want you to take your calculator. We're going to find the maximum possible elastic bending moment if you had a 2 by 4 centimeter beam out of A36 steel. Put that in your calculators. Tell me what you get.
Professor Griffin,
Yeah.
isn't that 200 gigapascals supposed to be 250 megapascals, because 200 gigapascals is the modulus of elasticity and not its yield stress?
Honkin, thank you. Who is that that's helping me? Who is that?
This is Samuel.
Samuel, thank you, Samuel. This is wrong. Samuel is absolutely right. This is 250 megapascals. Samuel is on the ball. Now, plug that in and we'll get it right thanks to Samuel. What would I do without you guys? Well, I've got my answer. Now, did you guys get 1,333 Newton meters? And if you did, say, uh-huh.
That's what I got.
Yay. Give me another uh-huh.
Yeah,
Uh-huh.
about the same.
Okay, we have just found the maximum possible bending moment that this thing could take and still be elastic. Now, if you make it any bigger than that, it goes plastic. Let's go plastic. Let's go, in fact, let's go fully plastic and we'll calculate that. Here, I need a little room here. I'm going to redraw this thing. It's actually simpler when it goes fully plastic. Now this here is wrong. It's 250, isn't it, Samuel? Let me put the right number in there. That must have been from that problem I was doing with Mohammed a little while ago, huh? I don't know what it was, but it's 250 megapascal, and Samuel helped us out there. Okay, now if you go fully plastic, then here's your 2x4. There it is. It's 2 centimeters this way, 4 centimeters this way. And what happens when you go fully plastic, it starts up here. You get plastic up here of tension, and it builds, and pretty soon this entire upper half is, well, here, I'll try to draw it. It's all, you've got the yield strength on the entire upper half. But now on the bottom half, you have compression. You have the yield strength, I'm sorry, but you have tension on the bottom, compression on the top, and we can get the bending moment. Here we go. And now this is going to be called the fully plastic bending moment. Now what we did before was the maximum elastic bending moment, but this is going to be the fully plastic bending moment. And we're going to get it for this same beam here. Now let me get my red color here. And the resultant of this distribution, it's a force. It's really, these forces are three-dimensional because they're pushing on every part of the, you understand? They're pushing on every part of this beam, cross-section. And so what you have to do is you have to take your yield strength, normal stress times that area there. Now that area is 0.02 meters squared. You know how it works. Stress is equal to force divided by area. So force is equal to stress times area. Stress is force over area. So force is stress times area. Okay, well this area is 0.02 meters times 0.02 meters. That's the force acting on the upper half of our beam. But now you also have a force this way, a resultant force. And that resultant force is equal to your yield strength times the 0.02 meters squared also. Same thing. Now we have something called a couple. And you guys all know what couples are. They're two equal and opposite forces separated by a distance. And this distance between them happens to be, let me think, I think it's 0.02 meters. So the moment caused by that couple is going to be, here we go, this will be the fully plastic bending moment. It will be your force, which is sigma y times 0.02 meters squared. That gives you your force, times the distance between them, which is 0.02 meters. That's how you figure couples. You take the force times the distance and you get the couple. Okay, well, this will give us our fully plastic bending moment. Let's see what that is. I could almost do that in my head, but not quite. Now let's go ahead and put in this amount. They said this was 250 megapascals. I think it was Samuel that helped me out on that. Remember the 250 megapascals? Put 250 megapascals in here and multiply by 0.02 times squared times 0.02. Here it goes. 250 e to the 6 times 0.02. It's really cubed, isn't it? Well, did you get 2,000? Did you get 2,000 Newton meters? That's what I got. I got 2,000 Newton meters. Well, you know what? That's bigger than 1,333 Newton meters. But remember, this is what you have if you're still barely elastic. But if you increase the bending moment to 2,000 Newton meters, it's completely plastic. Of course, once that happens, it's soft like butter and it just collapses. You've got yourself a major problem. Now, there's an interesting relationship. If you have a rectangular beam, it turns out, there's some room down here. Let's do this. It turns out that if you take the fully plastic moment and you divide by the maximum elastic moment, you get 1.5. Try it. Take 2,000. What is 2,000 divided by 1,333? Try it. Let's see what you get. 2,000 divided by 1,333. Boy, Chew, you get 1.5. If you have a rectangular beam, that ratio is 1.5. They have a special name for that. They call it the shape factor. That's called the shape factor. Now, this is only true for rectangles. If you have a rectangle, and a lot of beams are rectangles, the shape factor is 1.5. But there's other kind of beams, hundreds of different kind of beams, and they can have a different shape factor. Now we've got two extremes now. We've got the maximum elastic bending moment and the fully plastic bending moment. Let's write the general equation for this fully plastic bending moment. And let's see if I have, I just need some room here. Here's some room. The general equation for the fully plastic bending moment for a rectangle would be the force, which is the yield strength, times that area, which is base times the height over 2. You know, and then, see, that's the force. And then the couple that distance there turns out to be h over 2, I believe. Didn't we say that? Yeah. I think that's it, guys. Let's see what we get. Oh, yeah, that's it. Now this is the fully plastic bending moment, just in algebra. And here's what you'll get. You'll get 1/4 BH squared sigma y. Now look in your book here and see if you can find an equation like that. Look on page, let's shop around here. Look on page 346. On page 346, kind of up in the upper third of the page, I see a 1/4 BH squared sigma y. Yeah, that's called the fully plastic bending moment. Okay, good. We've done good. Now here, let me kind of sum this up and maybe we could work some problems. That'd be good. We have something called the maximum elastic bending moment. And it's equal to, I think we said 1/6 BH squared sigma y. I did that from memory. Did I do that right? Don't let me, yeah, that's right. And then we have what we call the fully plastic bending moment. And that turns out to be 1/4 BH squared sigma y. And that's on page 346. Yeah, there it is. But see, there's a whole range of things in between. Now, the ones in between are called elastic plastic bending moments. They're partially elastic and partially plastic. You'll see a lovely picture of those on page 345. On page 345, you'll see it goes plastic up at the top, but it's not totally plastic. You still have an elastic region kind of in the middle. Here, I'll draw it for you. Do I have room? Yeah, kind of. What happens is you have a region here that's plastic, and you have a region here that's plastic, but it hasn't gone completely plastic. You still have an elastic region in the center of your beam cross section. You'll see that on page 345 in your book. Take a look. There's an equation for it. Now, if we had more time together, I would love to derive this equation, but we don't have more time together. But they do it in your book. You could read the book. It wouldn't hurt you. It's on page 345. And this equation goes like this. Starts off kind of reminiscent of what we were doing here, 1/4 BH squared sigma y. But then it's got this other term. Hope you can read my writing. That's the equation for the elastic plastic torque. You know what B is? It's the base of your 2x4 or whatever it is, and the height. You know that's the height. And we know what that sigma y is. That's your yield strength normal stress. That's where it yields. But what is this y sub y? What that is it's the distance from the centroid to the beginning of your plastic region. There's your y sub capital Y. That's it. That is the, I hate to call it radius because radius depicts, you're talking about a circle, right? We don't have a circle here. It's the distance to your plastic, where your plastic region begins. Okay, well, great. Let's go back to our example that we just did. We're going to use this equation on that example. Do you remember, we're talking about plastic bending moments now. Do you remember that the maximum elastic bending moment was 1333 Newton meters? And the fully plastic bending moment was 2000 Newton meters. Well, let's do one in between. Let's pick a number between 1333 and 2000. How about, I don't know, how about 1500? Suppose you had, now, you know what this would be? This would be an elastic plastic bending moment, wouldn't it? 1500 Newton meters. That's in between 1333 and 2000, isn't it? Okay, well, let's plug that in and we'll find the distance to the plastic region. Here we go. We have the equation. It's 1/4. Now the base on our 2x4 is 0.02 meters. And the height, remember, was 0.04 meters. And you have 1 minus 4/3. The distance, this y sub y, is the distance from the centroid to where the plastic region starts. And then the h is 0.04. Okay, now here we have an equation with only one unknown. And that is that y sub y. It's the distance from the center to where the plastic region starts. I'm going to shut up for a minute and a half. I want to see if you can find it. Go ahead and we'll do it together. We're talking about elastic. Go ahead.
The formula.
The formula. Did I do it right?
No, I'm saying you forgot the yield strength to put in the formula. Sigma y in the
did I forget that sigma y?
Yes, on the top.
I
Yeah.
forgot it. Dang. Here, let me put it in. I forgot it. Thank you. Point for Mohammed. It's 250 megapascals. And then it's 1 minus 4/3. Thank you so much, Mohammed. Y sub y squared over 0.04. Now I think I got it right. Plug that in and get it for me, would you please? You have a minute and a half. Okay, well, that probably gave me enough time. Let me see what I think it is. All right, 1,500. Well, I got an answer. I wonder if this is right. Did anybody get solving this? I could be wrong. Did anybody get a distance from the center to where it goes plastic of 0.086, a bunch of sixes? Anybody get that?
That's what I got.
Let's see if that even makes sense. uh, see this distance right here. That distance is 0.020. Well, that can't be right. That's too big. That's too big. 0.08.
Is your h supposed to be squared in your formula? The 1 minus 4/3 y squared over 0.04.
That's supposed to be squared, isn't it?
Yeah.
Now, who is that helping me now?
Ashley?
Ashley gets a honkin' thank you point. This is wrong. And see, it didn't make any sense. It's going to be smaller than 0.02. So let me do it all over again. Thanks to Ashley, I got the right numbers this time. Good going, Ashley. Well, what would I do without you guys? Okay, I got an answer that makes sense this time. This time I'm getting 0.01732 meters. How about you guys? See, you know where that puts
That's what
me?
I got.
Yeah, look where it puts me. It puts me right about here. 0.01732 meters. Yeah, and so see, here's the deal. You get this plastic region here, and then you get a pretty big elastic region. All of this in the middle is elastic. And you have a plastic region at the top and the bottom. It's an elastic plastic torque. The 1,500 Newton meters is in between totally elastic and totally plastic. It's partially elastic, partially plastic. Any other comment on that? Well, great, we're making progress here. Well, let's do something other than a rectangle. Now, you guys got to know something, that these equations, you see these three lovely equations that we came here. In fact, we derived them, you know what? We derived those equations. Those are only good for rectangles. If you don't have a rectangle, those equations are no good. Well, let's do something without a rectangle. Here we go. We're going to try something else. I need some room to do this. But is there any other, before I do something else, I think I'll do a circular rod. But before I do that, any comments or questions on the elastic plastic moments of rectangles? Well, okay, we're going to do a circular cross section now. Let me erase all this stuff. Those are wonderful equations we have there, but they're only good for rectangles. What if you have something else? Like, for instance, one of these. In fact, we did one of those. Mohammed had me do one of those earlier. Now that is made of rectangles. There are rectangles in there, but that is not a rectangle. In fact, they have a name for that. They call it a wide flange beam. We have tables with a lot of information about wide flange beams in the back of your book. And maybe we can work on that, but right now we're doing circular cross section. And we'll start with the maximum elastic bending moment. And the name of this is the maximum elastic bending moment. But see, it's not 1/6 BH squared sigma y anymore. See, that's only good for a rectangle. I don't think we're going to have the same formula now. That's just for rectangles. What are we going to do when we have a circular cross section, like a rod? We could have an A36 rod. In fact, why don't we do one with the Ingles, senor? So suppose this is a 2-inch diameter. 2-inch diameter A36 rod. That'll support a lot of weight. Heck yes. You could build a tiger cage out of that. You could build a buffalo cage out of that. I don't know if you've ever seen the fences that they build to keep the buffalo in, or the bisons, I guess is what they really are. But they better be pretty strong, because those babies can run right through a barbed wire fence. Okay, well, how are we going to get this? Well, here's what we could use. We could use this equation here. Now that equation has a name. Let me ask one of my excellent students here if they can remember the. Nicholas, unmute and say hello, please, Nicholas.
Hello.
Hello. Hey, Nicholas, this equation has a name. It's probably the most important equation in this chapter 6. What's the name of it? He's thinking.
Look at it. I don't know.
I'll give you a hint. It starts with F. Starts with F. Starts with FL. It's got an X in it. Come on, Nicholas, you know this.
I don't know it.
Nicholas, it's the flexure formula.
They all look the same.
They call that the flexure formula. Okay. Now, if you wanted the if you wanted this here, here's what you'll do. You put in your yield strength stress. And this here would be, have you ever noticed they use the symbol C? You know what C is? It's the maximum distance from the center. So you put in a C and then divide by the I. Well, what's the I for a circle? Well, just look it up. Go in the back and look it up. It is 1/4 pi r to the 4th, which in this case would be c to the 4th. Okay, guys, I found that 1/4. I found it in the flap of my book here for a circle. All right. So didn't we already do that? Isn't it? Well, wait a minute. You can't go 250 megapascals if it's in English, senor. You know what it is in English? I think it's 36 KSI. If you don't believe me, go to the back and look. 36 KSI. Yep, that's it. For structural steel. We're going to get this thing right here. Now, this thing here is called the maximum elastic bending moment. And so I can do that. I know that that's, well, that'd just be 1 inch, wouldn't it? For the, yeah, it's just 1 inch. This is 1/4 pi times 1 inch to the 4th power. Now be careful now about the units. When we get through here, this is going to be in inch pounds. It's going to be in inch pounds. Now I want you to go ahead and solve this and tell me what the maximum elastic bending moment is for a 2-inch diameter structural steel rod. I'll shut up. Go ahead. Okay, I got what I think the maximum elastic bending moment is. Let me ask one of my excellent students here. Julian, unmute and say hello, please, Julian.
Hello.
Hello. Did I give you enough time to plug that in and find that maximum elastic bending moment, Julian?
I'd actually stepped out of the room for a bit, so I gotta see what's going on. Sorry.
That's okay. Let me pick on Chase. Chase, unmute and say hello, please, Chase. Earth calling Chase. Come in, Chase.
Hello.
Hey, oh, there he is. Hey, Chase, have you plugged in this equation and gotten the maximum elastic bending moment yet?
I am still working on it.
Yeah, take your time. I'll check mine, make sure I got mine right here. Yeah, I think I got mine right. I'll give you a few seconds here, Chase. Any luck so far, Chase?
I'm about to have the answer real quick.
All right. I wonder if I did mine right.
I got 28.27.
That's correct. It's 28 points. Wait a minute, I got 28.27.
Yeah, that's what I got.
Yeah. Now, what are the units, Chase? I agree with your number, but we've got to know the units on this stuff.
I want to say KSI.
No, we're doing bending moments. Bending moments are not in KSI. See, stress is in KSI, but bending moments are not in KSI. What are they in? They're not KSI. This is good. This is good not only for you, Chase, but for the rest of them. They need to know that stress is in KSI, but bending moments not in KSI.
Those would definitely be in Newton meters.
Yeah, now wait a minute. Wait a minute. Again, now you're learning stuff here. If you're in English, you don't have Newton meters. Now, see, if you're in metric, yes, in metric you have Newton meters. But, senor, we are in inglés, por favor.
They'd
You don't
definitely
have.
be in pound feet then.
Yeah, it'd be what now?
Pound feet.
Yeah, there you go. Now, actually, when you do this, this turns out to be kip inches. Let me show you what you get. You get 28.274 inch pounds is what you get. Or you could write that as 28.274 kip inches. They're the same. Now, if you wanted foot pounds, we could get foot pounds. Just go a foot is 12 inches. Or you could come up here and you could go a foot is 12 inches. And what you'd have is 2356 foot pounds. And here what you would have is 2.356 kip feet. That's valuable stuff. I'm talking to Chase, aren't I? Is it Chase I'm talking to?
Yes, sir.
Yeah, Chase, this is valuable stuff. You're going to be dealing with stuff like that. I don't care whether you're a civil engineer, mechanical engineer, I don't care what you are. You got to know foot pounds, kip inches. You got to know about those. Okay, well, how are we doing? We have 4 minutes. I was going to do the fully plastic moment. We better hurry. What we just came up with is the maximum elastic moment. We got it. Yay, it's 28. We'll round it off to that because we're lazy. And we'll write kip inches on it. But you guys are learning some important stuff. Now let me show you the fully plastic moment, and it's sad, but our time together is coming to an end. You got some homework, it's on Blackboard. Now here's what we're going to do. Oh, I better hurry, I only got 3 minutes. You know that the whole top half of this thing is going to go plastic, and it's going to be compression. Here, I'll color it green. There you go. It's compression. And the force involved is going to be your yield strength times the area of half of a circle. Well, they taught me in school many years ago that the area of half a circle would be 1/2 pi r squared. If it's got a 1-inch radius, then it would be 1/2 pi times 1 inch squared. That will give you the force. And see, if it's compressive, that means you've got a compression force doing that. And it's equal to 1/2 pi 1 inch sigma y. There you go. But you also have a compressive force, I'm sorry, a tensile force pulling on the bottom. And it's equal to the same amount, 1/2, I better hurry, I'm running out of time, pi times 1 inch squared times your yield strength, which we know, by the way, it's if it's A36 steel, it's 250 megapascals. So we can get those forces, and the distance between them is a little bit tricky. If you go to the flap of your book, it says the centroid of a half circle is at a distance here. See that distance? It's at a distance of 4r over 3 pi. 4r over 3 pi. So this couple here is going to equal this force that we just cooked up right here. Yeah. Times that distance between the couple, which will be twice that. It'll be 8r, which is 1 inch, over 3 pi. That's the couple. Here's the force. What happened to my, I don't want an equal sign there. I want that there. That's the area. That times that is the force. And this is the distance between the couple. See, it's 4r over 3 pi for the top half circle, 4r over 3 pi for the bottom half circle, but the total distance is double that. That'd be 8r over 3 pi. Okay, I'm going to do that, and I'm going to get, oh gee, I'm out of time, but we'll steal a minute from you. And we're going to get the fully plastic bending moment. Remember, this is 250. I'm plugging this in now, 250 e to the 6th divided by 2. Now the parentheses goes here. Yeah, that's just a 1 squared is what that is. Divided by 2, divided by 3, times 8. Now, if I did that right, well, that can't be right. I did something wrong. 250 e to the 6th times, or divided by 2, times 8, divided by 3. Okay, that can't be right. Oh, gee, and I'm running out of time. Okay, now just a minute now. 1/2 pi r squared, that's the area. That's the stress, 250 megapascals, right? No. 36 KSI. I'm doing the same thing one of my excellent students did. They got the metric and the English mixed up. This is 36 KSI. Okay, now I'm going to do this right this time. 36 e to the 3rd divided by 2 divided by 3 times 8. That's more like it. I'm getting 4,800 inch pounds. In other words, 4.8 kip inches. That's your fully plastic moment. The fully elastic moment, what was that? Do you remember what that was? I had it on the board here. There it is. It's well, that can't be right. Was it 28.27 kip inches? Is that what we had? I think it is. Let me do this again. 36 e to the third divided by, it amounts to dividing by 6 times 8. 36 e to the third divided by 6 times 8. No, I'm getting 48. Oh, it's 48,000. Here's my problem. It's 48,000 inch-pounds. In other words, it's 48 kip inches. And this is 28.27 kip inches. There, now I finally got that correct. Now look, this is your fully plastic bending moment, 48 kip inches. And this is your maximum elastic bending moment. See, it's smaller. It's smaller. And if you want the shape factor, that's the ratio. Let's see what that is. It's not 1.5. It's 48 divided by 28.27. The shape factor is round it off, 1.70 for a round beam. And we had a lot of fun. You got homework to do. We're going to have to get out of here. Sayonara, adios, muchachos. See you on Tuesday at 9:30. Bye-bye.
Professor.
Bye-bye.